You know the device you're watching this on right now? Well, it's almost certainly powered by the ideas of one man, a man you may have never even heard of. His name is John von Neumann. Now, that might sound like a pretty bold statement, but it is absolutely true. From the phone in your pocket to the servers in the cloud, his architectural blueprint is, well, it's everywhere. It's kind of like the ghost in the machine, that fundamental logic that makes all of modern computing possible. So what exactly is a von Neumann machine, and why should you care? Well, the answer starts, believe it or not, back in World War II, with a massive mathematical problem that was seriously crippling the Allied war effort. All right, Section 1, the trajectory problem. The challenge was simple to state, but incredibly hard to solve. Figure out where an artillery shell is going to land. The stakes? Oh, just winning the war. See, if you're firing an artillery shell for miles, you can't just point and shoot. You've got to aim high, letting the shell fly in a big arc, a parabola, to hit its target. But how high, exactly? Well, that changes with distance, with the wind, the air temperature, even the rotation of the Earth. What you need is a huge book, a table of pre-calculated trajectories for every single possible scenario. And this is where the sheer scale of the problem just becomes mind-boggling. Each one of those firing tables needed about 3,000 different trajectories calculated. A team of 100 human computers, and yep, computer used to be a person's job title, would take a full month to finish just one table. The war was not about to wait a month. And the technology they had at the time, it wasn't helping much. These clunky mechanical calculators like the differential analyzer, which was all gears and wheels, were actually even slower. The U.S. Army's ballistic research lab was hitting a wall, and they were hitting it hard. They were desperate for a breakthrough, for any way to speed up the math. So Section 2, ENIAC, the electronic giant. And that breakthrough? Oh, it came. And it came in the form of a 30-ton, room-sized electronic behemoth. Built in total secret at the University of Pennsylvania, ENIAC was a genuine revolution. It was funded by the Army, designed by John Mauchly and Presper Eckert, and it was an absolute monster of vacuum tubes and wires. But here's the thing. It was a fast monster. It could crunch numbers 1,000 times faster than any machine that had ever come before it. But who was actually operating this beast? Well, the very first programmers were 6 brilliant women. But their work was so unappreciated at the time that when the first photos of ENIAC were released, they were literally mistaken for models, just pretty faces posing with the machine. Their absolutely crucial role was basically ignored for decades. But ENIAC had a huge, glaring flaw. It was a powerful calculator, for sure, but it wasn't a computer like we think of one today. To give it a new problem to solve, you didn't just type in some code. No, you had to physically get in there and unplug and replug thousands of cables and flip hundreds of switches. This programming process could take weeks, all for a calculation that the machine might then spit out in a few minutes. It solved one problem but created a massive new one. Section 3, a chance meeting. The solution to ENIAC's biggest problem didn't come from its designers. It came from fate, from a completely random encounter on a train platform. And this is where John von Neumann walks onto the stage. We're talking about a real-deal genius here. This is a guy who could divide 8-digit numbers in his head at age 6. By the 1940s, he was a top mathematician working on the Manhattan Project. And just like the Army, he was getting incredibly frustrated with how slow the calculations for the atomic bomb were taking. History can turn on the smallest moments. And in August 1944, one of those moments happened. Herman Goldstein, who was the military guy in charge of the ENIAC project, was just waiting for a train. He bumps into von Neumann, who he knows. Goldstein starts talking about this giant electronic calculator he's working on, and von Neumann, who was desperate for more computing power, was immediately hooked. Now, it is really important to point out, von Neumann didn't just pull these ideas out of thin air. He was hugely influenced by the theoretical work of Alan Turing. But man, personally, they could not have been more different. Von Neumann was Johnny, the extrovert who loved throwing parties and drove a new Cadillac every year. Turing was this quiet, solitary genius who wore a shabby coat. But despite their differences, von Neumann always gave credit to Turing's abstract idea of a universal computing machine as the real foundation for his own practical work. Section 4. The Blueprint for Modernity. Because after von Neumann saw ENIAC, he realized the goal wasn't just to fix its problems. The goal was to write the blueprint for every single computer that would come after it. And that was the key insight right there. It wasn't about building a better calculator. It was about totally rethinking what a computer could and should be. So his first revolutionary idea was to use binary. See, ENIAC was decimal-based, which meant it needed really complex hardware to represent 10 different digits. Von Neumann saw that the simple on or off nature of an electronic switch was a perfect, natural fit for a language of just ones and zeros. It was simpler, cleaner, and way more reliable. But his second idea, now this was the masterstroke. This was the real game changer, the stored program concept. To fix ENIAC's biggest headache, that whole weeks of rewiring thing, von Neumann proposed storing the instructions, the program itself, inside the computer's memory, right there alongside the data. The program and the data would live together. And just like that, the machine could finally operate itself. He laid all of these ideas out in a 101-page paper, which became legendary, the first draft of a report on the EDVAC. Now, his was the only name on it, which caused a fair bit of drama with Eckert and Mauchly, but that report got distributed far and wide. And it essentially became the definitive blueprint for the entire digital age. Section 5. The von Neumann Legacy. And let me tell you, the ideas in that report did not stay on paper for long. They kicked off a digital big bang. The adoption was almost immediate. It was incredible. By 1951, Eckert and Mauchly's commercial computer, UNIVAC, was built on these concepts. By 52, the IS machine at Princeton was finished, and its designs were shared with everyone. Then, by 1953, IBM releases its first big scientific computer based on that machine. Suddenly, everyone was building a von Neumann machine. And that fundamental structure, CPU, memory, input-output, that's the von Neumann architecture that is still the bedrock of computing today. Ultimately, von Neumann's true genius was to separate the thinking from the machine itself. He turned programming from a physical act of moving wires into a logical act of writing software. He transformed a tangled mess of hardware into the elegant logic of code. And in doing so, he unleashed a revolution of power and complexity that we are all still living through today. He solved the great computational problem of his day. And that leaves us with one final thought to chew on. The von Neumann architecture has served us amazingly well for over 75 years, but it's starting to show its age, to hit its limits. So the question is, what is the great problem of our time? And what new architecture, what new revolution in thinking will it take to solve it?